Alright, let's start by walking through what GRPO actually is and why it matters in large language model training. So, GRPO stands for Group Relative Policy Optimization. It's a reinforcement learning method, but it works a bit differently from what you might have seen with traditional PPO. Instead of using a separate value network to estimate rewards, GRPO compares multiple outputs generated by the model itself for the same prompt. In simple terms, the model doesn't need an extra critic to tell it what is good or bad. It just looks at its own group of outputs and learns which ones performed better. Now, here, the big thing here is efficiency. And GRPO cuts memory usage almost in half compared to PPO because it removes the need for that separate critic network. It relies on group-based advantage estimation, meaning it evaluates each output relative to others in its group. And this approach is what allows DeepSeek R1, for example, to perform advanced reasoning without needing massive infrastructure. And yes, you can think of GRPO as a smarter, lighter version of PPO. It does the same kind of reinforcement learning update but without the heavy overhead. And let's talk about its impact. What are they? GRPO makes reinforcement learning accessible to a lot more people because it can run on standard hardware. Models trained with it, like DeepSeek Math, showed clear improvements in reasoning benchmark and on GSM8K, for example, accuracy jumped from about 82.9% to 88.2%. And because it's so resource friendly, you can actually train reasoning models with just a 16 gigabyte GPU, which is pretty rare in this space. And it even makes it possible to get competitive results for under $100 of compute costs, which is impressive for reinforcement learning based training. And here we have a comparison. With traditional PPO, we need a value network, also known as a critic, and this critic estimates how good each action or token is, which doubles the memory footprint. And it is also computationally expensive because it requires calculating per token value estimates across long text sequences. And why it is important, let's talk about it. That's the kind of setups used in early ChatGPT training. On the other hand, GRPO skips all that. It doesn't use a value network at all. Instead, it calculates a baseline directly from the group of samples outputs. And by comparing rewards among these samples, it figures out which responses are better or worse relative to the average. The update then uses that information to guide the next policy step. Because it doesn't train a critic, GRPO uses roughly half the memory and converges faster. And if you look at the highlighted section here, labeled Core Innovation, that's exactly the essence of this method. Instead of explicitly learning a value function, GRPO estimates advantage by comparing rewards within a group. And that's why it's both simpler and more memory efficient while still maintaining training stability. And how it works, let's talk about that. Step 1. We generate multiple responses for a single prompt, and let's say you give the model a question. It doesn't just produce one answer. It generates a set of possible answers, maybe 8, 16 or even 64 of them depending on the group size. And step 2, each of these responses is scored using a reward model, and the reward model might evaluate correctness, coherence, or how close the answer is to the desired results. And then in step 3 we calculate what's called the relative advantage. For each response we'll look at how much better or worse it's compared to the group average. So if the mean reward is say 5 and a particular response scores 8, its advantage is positive. If it scores 2, its advantage is negative. And finally, step 4 is a policy update. Here we use those advantages to adjust the model's parameters, and the update is clipped, meaning we limit how far the model can move in one step to keep training stable. And there is also a KL term which measures how much the updated model deviates from the previous version, preventing it from drifting too far. And let's run it, and let's make it 64. So when you look at the reward distribution chart below, you can see these rewards vary among the 64 samples. The mean reward here is around, what is that, and 5.22, and standard deviation is about 3.33, and that spread shows how diverse the responses are within the group. You can see here, and right under it there is a scatter plot for the calculated advantages. Positive advantages mean that those responses performed better than average, while negative ones performed worse. And this visualization makes it clear which samples the model should reinforce and which ones it should discourage in the next update. Okay. And advantage calculation is here. Let's look at this. GRPO defines it as A hat of I equals R of I minus mean of R divided by standard deviation of R here. And what this means is for each response we take its reward, subtract the average reward across the group, and then normalize it by the standard deviation. That normalization ensures that the scale of rewards doesn't dominate learning. And let's look at our basic example here. The question is, what is 5 plus 3? Response 1 says 8, which is correct, so it gets a reward of 10. Response 2 says 7, which is wrong, so it gets 0. If we calculate the mean reward, it's 5, and the standard deviation is 5 as well. When we plug those into the formula, the first response advantage becomes positive 1 and the second becomes negative. And here, and example 2, capital of France, and here Paris, London, here positive, positive, and here discourage. And let's continue. Okay, training process. Alright. When we talk about GRPO training process, what we are really describing is how the model updates its behavior over time using reinforcement learning. In the interface you see here, there are two key hyperparameters that guide this process: the learning rate, which we call alpha, and the KL penalty, which we call beta. And the learning rate alpha equals 0.00003 and controls how big each update step is during training. If it is too large, the model might overshoot and lose stability. If it is too small, training becomes slow. So we use a small value here to keep progress steady and controlled. Then we have the KL penalty here, beta equals 0.01, And this is the coefficient that penalizes the model for drifting too far away from its reference policy. Basically, it keeps the new model from becoming too different from the version it started with. And without this penalty, updates could be aggressive, and the model might forget previously learned patterns. By the way, let's run it. If you look at the GRPO objective function shown on screen, it's written as like that. What is that? R equals the expected value of the minimum between ratio times A and the clip version of ratio times A minimum minus beta times KL. Let's unpack that. The ratio here is the new policy's probability of generating a given output divided by the old policy's probability for the same output. And that tells us how much the new model is shifting its behavior. And the A represents the advantage value, which we have already seen is calculated from the group-based comparison. And the clip term limits how much this ratio can move in one update. That's our safety mechanism. So what this objective does is balance learning progress with stability. And it increases the possibility of good responses while keeping changes bounded and penalizing excessive deviation through the KL term. And here you will notice the safety mechanism sections. What is that? Clipping and KL divergence are both there for a reason. Clipping with epsilon equal to 0.2 ensures we don't let the policy jump too far in a single step, and KL divergence ensures the policy stays close to the previous model or reference policy, and these together keep GRPO training predictable and smooth. And let's look at our training progress. The green line represents the average reward over training iterations, and the red line tracks KL divergence. As you can see, the average reward gradually increases from around 3 to almost 8 over 50 iterations. That means the model is learning, it's producing better responses on average. Meanwhile, the KL line stays flat and low, which shows that the updates are stable and the policy is not drifting too far away from its original behavior. And this kind of steady improvement with low instability is exactly what we want to see in reinforcement learning. And here, applications. So what are they? The first one is mathematical reasoning. This is where GRPO really showed its potential. And in the DeepSeek Math project, applying GRPO improved accuracy on standard reasoning benchmarks. For instance, GSM 8K accuracy went from about 82.9% to 88.2%, and on the math dataset from 46.80 to 51.7%. Those gains came without using massive compute clusters, just smarter training. And the group-based advantage method fits perfectly for training tasks because each output can be easily verified for correctness, giving clear feedback to the learning process. And code generation is here. GRPO is also used to train models that write better code. And here, the reward signals come from testing, whether the program runs correctly, passes tests, or fixes bugs. Our repeated iterations, the model learns to write cleaner and more accurate code. You can think of this as a reinforcement loop for coding. The model generates code, it gets scored, then it improves based on those scores. And finally, reasoning models. This category includes large models like DeepSeek R1, and these models perform multi-step reasoning, break problems down into smaller parts, and even reflect on their own output. GRPO's relative comparison mechanism fits perfectly here because Reasoning problems often don't have smooth gradients to follow. They require discrete evaluation of answers, and the algorithm helps these models become competitive with high-end systems such as GPT-4, but at a fraction of the cost. And finally, let's talk about why GRPO matters. We can say that democratization, GRPO makes reinforcement learning available to people who don't have access to large compute clusters. You can train reasoning models on a single 16 GB GPU for under $100, and that's a huge shift in accessibility for research and development. And second, efficiency. By removing the value network, GRPO cuts memory usage roughly in half while maintaining stable updates. And that's a big deal for smaller labs and individuals who need to train models efficiently. And simplicity is here. The algorithm is straightforward to implement, and instead of maintaining a separate critic model, we just calculate group-based advantages. That means fewer moving parts and fewer changes for implementation errors. And finally, performance. GRPO achieves strong results on reasoning tasks and mathematical benchmarks. It powers on, I mean, it powers open source models like DeepSeek R1 that can compete closely with proprietary systems without needing the same scale of infrastructure.